All right, I think it's been a little bit longer than 5 minutes, but let's go ahead and start. I wanted to find a few things to show you. First of all, let me go into the next presentation and talk just a little bit about programmable logic controllers. I went to the next room. I used to teach this class in the next room over, so all my toys are kind of over there. I need to move them over here sometime. But these are PLCs. Each one of these is a programmable logic controller. Now, these are fairly old PLCs. Allen Bradley, fairly old. They're modular designs, so each one of these cards can be slid out. Basically, it's a backplane design. The main power supply and computer for this particular one are here. Sometimes the power supply and computer are separate in the main brain. But there's various input-output cards that are added to each of these PLCs. That's one way that a PLC can look. Another way is this way. This is Micrologic. This is also an Allen Bradley PLC. It's a little more modern. I'll pass this one around so you can look at it. You can flip open the doors and see the screw terminals. You attach wires for inputs and outputs. We'll understand more about this later. Just pass that around and have a look at it. I've got some other toys I'll pass around here in just a minute. Well, let's talk about programmable logic controllers. There's an SLC 500 sitting over there on the cabinet. I couldn't bring it because it's got a bunch of wires connected to it. It basically looks like this. Same idea. You've got it's in the other room. It's a backplane computer, and you can plug modules into it for input-output modules. So same idea as this. So anyway, like I said, PLCs are basically just ruggedized, industrialized computers that control input and output. So you give them input, they give you output, and hopefully you program it right so that makes the machine work. They're being overtaken by computers that are even more powerful. The big name is Compact Rio. Anyone ever heard of Compact Rio? Well, Compact Rio is basically the same format essentially as a PLC. It's also a ruggedized computer with a whole lot more capability, much more memory, much faster processor, all those things. You program it in a higher level language. What we're going to learn in this class is something called ladder logic. Okay? How many people have been exposed to ladder logic? Anyone? So you should be okay with it. But anyway, Compact Rio, you program in a different language. Usually you can program it in LabVIEW. That's just one particular company. Initially, PLCs were used to replace relay logic. Okay, I don't know if you guys know what relay logic is, but it used to be that there were cabinets full of relays that controlled stuff. And in fact, a good friend of mine works in the elevator business. He has his own elevator company where they go, they'll install, they'll repair, whatever. And he's told me that a lot of the buildings in downtown Louisville still use old relay controls. They don't have PLCs. So when you press the button, the light comes on, that's a relay kicking in somewhere. Okay? And they've got literally thousands of relays to control the elevator, make it move up and down, make it open and close the doors, make everything work like it's supposed to. Because if you think about it, there's a lot of inputs on an elevator. So you've got a 20-floor elevator, well, you need 20 buttons in the carriage to determine where you want to go. Not only that, but you usually have a door open and a door closed button, an emergency button. So that's already 23 inputs right there. Okay. You also have inputs on each floor to call the elevator, button to push to say, hey, I want to go up or I want to go down. So there's another 40, because, well, not 40, it would be 40 plus 2, so 38. Because each floor would have an up and a down, except for the top floor, it would have a down button, the bottom floor would just have up. Right? So there's, what, 60 inputs or so already, more, that you need to accommodate. And then you have to have doors that open and close on the elevator. That's one output. You've got to turn on the elevator to move up or down. That's two different outputs usually. Okay? Now those are not the only outputs. Once you start adding up all the lights that have to come on with all the buttons, now all those buttons we counted a minute ago, now there's 60 outputs to turn the light on and let the user know, okay, I know you've pressed the button. Right? So anyway, there's a ton of inputs and outputs, and all of those are controlled by relays. So the control cabinets for these things are huge. You know? Something that's the size of this wall would not be unheard of. And troubleshooting something like that is a real pain in the you-know-what, because if one relay is messed up, you've got to find out which relay it is. Okay? And all the logic for determining how the thing works is programmed via wiring. Okay? Sounds like a real pain, right? Well, it is. That's why he has a company doing it. Now, why do people keep these things around? Because really, you could replace all of that with a PLC. Here's a PLC. The PLC just needs a few contactors for motors, a little bit of wiring, and you're ready to go. It's a lot simpler because really the PLC is like having millions of relays inside of one box. Instead of making a bunch of wired connections, you program it. Okay, so it's a much better scenario. So why don't all of the buildings downtown Louisville replace their relay logic with PLCs? Basically, if it's not broke, don't fix it mentality. And also, if it is broke, fix it anyway because it's cheaper than something new. In the long term, it's probably not, but whatever makes money. Right? All right, so basically the PLC, thank you. Did everyone get to see this? Anyone miss it?
We didn't.
You got it?
Yeah, we didn't.
You didn't? Okay. All right. So as I was saying, basically the PLC replaces a bunch of different relays and you program it in something called ladder logic. It looks kind of like this. I'll show you some code here in just a minute. Okay, but it's also much more reliable because the silicon, the things that the chips are made out of, are much more reliable than mechanical motion of a switch going back and forth in relay. Okay, it's just a much better solution. Also, there's a lot more flexibility. It's much easier to change the programming in the PLC than it is to rewire some relays. Okay? It's a whole lot easier. Also, you can connect any kind of input or output essentially that you want to the PLC. We'll learn more about the details of that a little later. Also, it's usually lower cost. After you've paid for 10 relays or so, usually you can buy a PLC for that price. Okay? There's really no point anymore in designing with relay logic. Speaking of relays, I'll pass around a couple of relays as well. This is two different manufacturers. This was Phoenix Contact. This one is Square D. The relay is also Square D. But it's got a terminal block and relay connected together. Basically, this hooks onto a track, a standard track, and to replace what's called an ice cube relay, that's what this is. You just activate that. If the relay's bad, you can plug another one in. And then to make connections to it, you got a bunch of terminals. That's why it's a terminal block that you can screw wire into. So anyway, I'll pass that one around. This one's a little more simple. It doesn't have a fancy lever on it. You just pull the ice cube relay directly out. Okay, and it comes out that way, and you've got terminal screws here you can connect to. So a little bit simpler setup. We'll talk a lot more about relays. I imagine the ECETs know exactly what a relay is. METs you may know. But you'll know exactly what that is. The point is, these are not cheap. And after you pay for a dozen of these or so, you could have bought a PLC for the same price. Now, I will admit that relays do have one small advantage. Usually relays can take more current than the contacts on PLCs output. But if you get relay outputs on the PLC, then that's kind of a neat thing. But anyway, we'll talk more about that as well a little bit later. Another nice thing is communications capability. A PLC, unlike relay logic, can communicate. You can have an Ethernet port, and you can sit at your desk and program this thing remotely. It's really nice. You can monitor what's going on with the PLC, so if there's some type of error and some code can be sent to you, you can figure out what the error is and correct it. So PLCs by far are superior to relay logic. Another nice advantage is that they have much faster response times because the switches that occur are all digital switches inside of a chip, right? They're not a contact that has to physically move and take time to move. Okay, so PLCs give you much faster response time and better control that way. By the way, some people still enjoy dealing with relays, and I want to show you a video of a person that I respect a lot. I wouldn't bother doing this. Anyone else need to see the PLC? I really respect his work. He did a whole lot of work. This is not Harry Potter, this is Harry Porter. Okay, Harry Porter's relay computer. He built a computer out of relays, which is quite an undertaking. Let's see, let me full screen. Do we have sound on this computer? We do. The amplifier and speakers are on. Well, I can talk through it. Basically, he's talking about the various components. If you know what an arithmetic logic unit is, okay, he's got one in one of these boxes. Okay? He's got a whole 16-bit data bus, and he's programming it right now by flipping switches to put a whole byte into memory, for those of you who know what that is. By the time you're done with this class, you'll know what it is. Anyway, so he's describing the various registers that the processor has, okay, and how the whole thing works. He's got some memory off to the side. And in a minute, he turns it on, and you can actually hear the frequency of the computer because you hear the relays going clack, 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 clack. And that's the frequency that it runs at, okay? Basically, you guys have all bought a laptop or a desktop computer, and you know something about gigahertz or megahertz speed of the processor, right? Well, that is essentially how many cycles per second that computer can operate. Okay? So if you buy something that runs at 3 gigahertz, that means that the processor performs 3,000 billion, right, because it's 10 to the 9, operations every second, okay, or cycles every second, okay. This is operating at a speed of about 5 hertz or so, probably 5 relay clicks per second. This is a very slow computer by comparison to what you have sitting in front of you. Obviously, he's doing this as a hobby. The video is somewhat grainy, but if you look at it on your screen, you'll actually see the individual relays, and with a better screen than this projector, you can see the lights coming on and going off to indicate what's going on. It's interesting to watch. Yeah, you can kind of see the lights turning on and off now, but basically you're watching the computer operate. It's doing all its calculations with relays. Okay? That's quite an undertaking, quite an accomplishment, but I personally don't want to do it. But you can see this is a very rudimentary computer. This is very basic, okay? And yet, he's got just right here 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 or so, about 50 relays just in that section. That's just part of one box, and he has multiple boxes of these relays. Okay? You can see how quickly relay logic could be replaced by a fairly small computer. Let's see. I try to intersperse a few videos here and there to keep you interested. And like I said, there will be a lot more excuse me, hands-on programming as soon as we get a little bit of information under our belts. All right, so anyway, PLCs have it all over relays. It's not hard to argue. They're easier to troubleshoot, and usually the way you do it, you've got the PLC operating the line, whatever the process is. And usually the way you do it today is you hook a laptop up to the PLC, you download the program, figure out what's going wrong, and change the program on the fly, upload it, and you're ready to go. PLCs are so cheap, by the way, that I have included one in my home. You'll get to know me, you'll know I'm kind of crazy. I do all kinds of home projects. I have, not for the fun of it, but for various reasons, I bought a boiler that is a wood gasification boiler. What you do is you put wood in it, and it heats up the wood so much the wood pyrolyzes, it generates smoke basically. And that smoke then is pushed down through a nozzle at the bottom of the unit where secondary superheated air is injected, and then it burns as a flame. It's a very clean burn. It's not like the smoke dragons you might see if you go out and drive the countryside. This is a very clean burning piece of equipment when it's running right. Okay? So it's my main source of heat for my home, so I load wood during the wintertime. But it's pretty easy because all I have to do is fill the upper chamber, which has a decent volume, and then I go to bed and it runs all night. That's not a problem. Saves a lot of money too on heating, by the way. But anyway, this boiler system, I confess, I got tired of loading the boiler, especially during the months where it's not terribly cold, but I needed just a little bit of heat. Because it turns out that the boiler actually works best when it's really cold outside. When it's really cold outside, it runs full steam, it burns the wood really well. But when it's not very cold outside, the fire can overheat, and so it shuts down oxygen to the upper chamber, and then I get smoke coming out of the chimney. Basically, smoke is wasted wood. I don't like having to go and get wood and load it up, even though I have a good source for it. I don't like doing that if I don't have to. So I bought a heat pump, right? Because I found one on Craigslist that was fairly cheap. It was a nice 2-stage heat pump. And then I realized I've got a small problem here because somehow I'd like to use one thermostat to control both systems. Now, the sane, easy solution is to use the 2 thermostats, right? But I'm not really sane. So I wanted to use one thermostat. So what I did is I hooked up one thermostat to a PLC that I bought from Automation Direct for about $100. It was actually cheaper than another thermostat. And I programmed the PLC to intelligently switch back and forth between the heat pump or the boiler, depending on whether or not the boiler was up to temperature and how hot or cold it is outside. So I found a use for PLC in my home. You probably can too if you really want to. They're cheap enough these days that you can actually afford one to use for some control purpose. So every now and then I'll go down in my basement, hook my laptop up, see how things are going, see if it's running right, and if there's something I want to change, I'll just change it. Make it easy. If I want to change the transition temperature, where I go from heat pump heat to boiler heat, I just program it. There you go. It's very easy to do. Let's talk about the parts of the PLC. Not that it's terribly important that you know this, but you need to understand it at least. Basically, a PLC is something that deals with inputs, typically from switches or sensors, and then sets outputs. There can be all sorts of outputs. There can be motor starters to run huge industrial motors, I mean electrical motors. There could be controls to start a combustion engine if you wanted to. Okay? There can be light outputs. There could be relays. There could be solenoids, pneumatic solenoids. That's a very common application. So basically, a PLC takes input from input sensing devices and sets outputs to output load devices. The way it does that is it uses a brain, if you will, a central processing unit, and it takes a program that you put in memory and operates, chooses what outputs to set on or off depending on what inputs are set on or off and the past state of those inputs. Because the PLC has memory and it can store, it can remember, oh, this input was tripped, okay, it was on, it may be off now, but that means I need to, for example, turn this output on and keep it on. There's ways to do that, and I'll teach you how to do that. But generally, you've got a power supply module that supplies power to the input and output module, supplies power to the central processing unit, and you need some kind of programming device to modify the program and make the thing do what you want it to. Okay? All right. Architecture is a term that's used to talk about the PLC and the software, the whole system that allows you to make a PLC do something. Open architecture is where you can easily connect devices from other manufacturers, so it's more of a standardized setup where you can find out information. Say you want to build a PLC, you want to start a company making PLCs, you might go for open architecture because there's already a huge user base. It's kind of like Android versus Apple. Okay, the Android system is more open. If you want to make a phone that runs Android, you can do it, right? Whereas with Apple, you can't just build a phone that runs Apple software, iOS, without contacting Apple and getting their proprietary information because they deal with a closed architecture. It's the same type of thing, okay, except that it applies to PLCs. Right. Open architecture is becoming more and more common. Closed architecture is slowly going away, but there's still a lot of closed architecture. Both Siemens and Allen Bradley have been closed architecture for a long time. I'm not sure if they're going towards open architecture or not. I know they probably don't want to. They won't be able to charge such exorbitant prices for their products anymore. But anyway, fixed I/O is the term that would be used for this type of PLC because you can't add any more inputs or outputs to this unit. What you see is what you get. Okay, this one has, let's see, inputs are on top. That's what the I stands for. And it looks like there are 12 digital inputs and 4 analog inputs. Okay? And on the output side, there are 8 digital outputs, and there are 2 analog outputs, 2 continuous outputs. But you can't add any more to this. You're stuck, right? If you need more inputs and outputs, you'll have to go buy another PLC if it's the one you own. On the other hand, if you buy a PLC like this, and you've got some empty slots, you can just grab another card, put it in, and voila, you've got more inputs or outputs, whatever you need. Okay? So fixed I/O is typical of small PLCs that come with a limited number. Now, small PLCs today are kind of bending that rule as well. I'll show you the PLC that I bought. Because if you do anything with PLCs, you'll come across a company named Automation Direct very quickly. Anybody ever dealt with Automation Direct? Anyway, they're basically I would say that in my time they were the website that single-handedly drove down prices on controls. But anyway, they've got a couple of nice little things. I bought their Toyo PLC for my home system. I think we've got some of them here. Although I prefer to teach Allen Bradley because that's more common out in the workplace. But anyway, basically what you do is you buy the PLC unit, which is essentially the brain. It comes with a few inputs and outputs. You can see them over here to the side. And what's neat about this is that on the side that you can't see, there's some connectors. You can actually slap some more input and output modules. You can daisy chain onto this brain, this CPU. So even though it's a small PLC, it's actually about this size, just not so long, you can add to it. And so the rules are kind of changing. But the classic small PLC, you were limited on the numbers of inputs and outputs you could have. Modular PLCs, or modular I/O, are more like this, where you can add cards and increase or decrease the functionality of the PLC. You may be interested in switch on and off type inputs, or you may be interested in measuring a voltage signal, or even a thermocouple signal. For my PLC at home, I had a bunch of on-off type of inputs and outputs that I needed to control. But I also wanted to bring in a signal from the outside. I wanted to bring in temperatures. So I set thermocouples on my boiler so I could measure the temperature of the water circulating in the boiler to know it was up to temperature to heat my home. I put a thermocouple outside so I could detect the outdoor temperature and intelligently switch back and forth the temperature. Because it turns out, when the temperature falls too low, the heat pump's not really all that efficient. Okay, it's a decent heat pump, but when the temperature goes down, it just doesn't operate very well. And so I set a cutoff point of, I think, 50 degrees or so. No, maybe it was 35, I don't know. Anyway, at that temperature, it will switch over and request heat from the boiler instead of requesting it from the heat pump. But I had to do that by including an I/O unit that could detect thermocouple signals and understand or interpret what the signals meant. Okay. Now, the power supply is a feature that's very important. A lot of times when you're speccing out a PLC, you have to decide how much power the power supply is going to supply to the CPU and all the I/O devices. Now the problem with that is that when you're initially buying it, and you think you need so many inputs and outputs, if you spec the power supply to just supply enough power for what you think you need, you're probably going to end up with a problem later, because you'll probably have to add on to the PLC, and then you won't have enough power. Okay, so a lot of times it's good to over-spec the power supply so that you can accommodate future expansion. Okay, the processor is typically separated. In these PLCs, I believe the power, I don't remember, I think the power supply and the brain are all together. But in most PLCs, the brain is separate, or the CPU is separate from CPU and memory, are separate from the power supply. So you have to decide how fast you want it to be, how much memory it needs to have, so on and so forth. But this is the part that performs the logical operations, essentially runs the program. Now here's a very important slide. Okay, all this stuff I've talked about so far is just sort of background information. It's nice to know, but I'm not going to test you on it. Here's what's really interesting. Here's how a PLC works. How many of you have programmed in other programming languages before? Okay, hopefully all of you. You're supposed to have a programming class before you get here. But honestly, it may actually hurt you and not help you. Because programming in ladder logic is very different from either functional programming or object-oriented programming. Okay? You know what those terms mean, and you've programmed in any type of language, get ready to bend your brain again, because ladder logic is different. Okay? In ladder logic, the program is continuously scanning through. It's not like it goes to a section of the program and then waits until something happens. Okay? You can't make it do that. Well, you can, but you normally don't. Okay? What it does is it runs through your program over and over. And the way it does that is it runs in a cycle. It reads the inputs. It goes out and checks to see what switches are pressed, what various inputs are true or false coming into the PLC. It calculates the outputs, so it executes the program, runs some diagnostics and communication stuff that you don't have anything to do with this part, but it's something that's kind of housekeeping for the PLC. And then it updates the outputs, so it sets the outputs. So when your program's actually scanning, the outputs will not be set. It's after the scan is done that the outputs are set. And then inputs are read again. Okay? So it does this continuously over and over again. Now that'll be important a little bit later when we're programming. And you know, how about if I just go ahead and show you what a program looks like. This is Logix Pro. And in Logix Pro, you can program the PLC that's sitting right here. It's made to look like a Slick 500, which is an Allen Bradley's PLC. And over here, you can drag in contacts. You don't know what these are yet, don't worry about it. I'll show you what they are later. You have coils, which are essentially outputs, and you can program this way by dragging and dropping and referencing various addresses. That's part of what I'm going to teach you. Okay? I want you to see what this looks like and what you can do with it. Now, this may look a little bit intimidating. I guess it could look intimidating because there's a lot of inputs and outputs. There are simpler simulations as well. I'll probably start you out with the door simulator. What I usually do, there's a couple switches here for inputs. There's some buttons that are inputs. There's a couple lights that are output. The motor outputs are probably the most important ones. And you can make the motor move up to raise the garage door or down to lower the garage door. Okay, so this is a fairly simple system, kind of where you will start. Where I usually end up is either here on the model line simulator, where students are programming this as a group, or on the elevator simulator. It's a 4-floor elevator with multiple inputs and outputs. You've got a whole control panel inside of the elevator. You've got buttons on the wall to detect when the user requests the elevator. You've got a switch at the top and at the bottom to detect when the elevator's gone too far. You've got a motor that can move up and down. You've got another motor for opening and closing the door. These are not trivial systems to program. But by the time you're done with this class, I expect that you will be able to program it, because these are the two projects that I normally run. Now, if we go with the Christmas display project this year, we won't do this, okay, because that's going to be a lot of work. These are a lot of work as well. I thought I would just go ahead, though, and show you the solution that my students came up with last semester when I taught this class. I've got my own solution as well, but I'm not good at keeping track of revisions in my programming. I confess, like I should be. So I don't know which is my most recent version. I'll open up one of my versions, but I don't guarantee that it's one that works. By the way, Logix Pro is a fairly old program, so it can be a little finicky every now and then. You've got to do things a certain way. So that's in downloads. So open, downloads, blah, 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 simulator. Okay, so this is my students' code. I had 3 or 4 groups, I don't remember now. But this is their code. Now the code goes for a little while. Each one of the lines is called a rung, and it's called ladder logic because it looks like a ladder. You've got the sides of the ladder on either side, you essentially have a bunch of rungs. Okay, so that's where it gets its name from. The reason that this language was developed is because it looks a lot like an electrical schematic, where the electrical schematic is set up so that you can actually read it and understand what's going on from, say, high voltage down to ground, okay, or across 2 legs of, say, 220 or an AC voltage. I've never seen a schematic set up that way. It's actually a really nice way to set it up because it makes understanding what's going on a lot easier. But anyway, we'll scroll through some of this. There's several pages of code. Keep going, there it is. So what, 27 lines of logic to control this system. I don't remember if they used any subroutines or not. No, it looks like the subroutines are playing. Now, this part over here looks a lot like RS Logix, which is the actual program that is used for programming Allen Bradley PLCs. This section over here is what's unique to Logix Pro. This is the simulated system. Okay? So let's just download it, run it, and see what's happening. The reason we have to download it is because we're simulating programming on the right-hand side of the laptop and downloading that program to an actual PLC that sits on the line and controls the line. So let's see what happens. Download, run. I knew I shouldn't have done that. The CD that I've got in here is not a really good one, and it won't let me run this. I'll have to run it for you next time. The CDs I've given you are the full versions. This one over here is running in the demo mode, so it won't let me run it. But basically, this was one of the solutions that worked. You hit the start button, and what it will do, it's not shown here initially, but there are bottles that come along that are taller. So some are tall, some are short, some are broken. So you have a broken bottle detector. You have a switch here to detect tall bottles and short bottles, and a bottle presence sensor. Well, you have to fill the tall bottles with the large fill, with it looks like orange crush, right? You got to fill the small bottles with grape soda for some reason, okay? But after you're done, you have to cap them. If it's a good bottle, it needs to be capped. And then at the end, you have to sort them large and small, whichever way you want to. If it's a bad bottle, you have to open up the gate and let the broken bottle fall, get crushed. You've got to turn on this motor. You've got to monitor how much glass is accumulated in the box, okay? And when a box is full, you've got to index the box and bring a new box around. So this is a simulation for a fairly complicated system. In the real world, this is a simple system. Okay? But for you guys right now, this probably looks overwhelming. Now, some students that have set in on the class because they were working on CAD or something, when I was teaching the course, they looked at it and said, oh, that looks like fun, because it's graphical. You know? And when I started doing it, they thought, oh, this sucks, because it's hard. All right, but anyway, this is the caliber of what you'll be able to do by the time we're done with this class. And don't worry, I'm not going to throw you in on the deep end yet. I will give you a lot of one-on-one help. One thing I asked when I'll go through that. All right, but if you looked at RS Logics, it looks like this. So this is exactly what it looks like, where you've got just information about the PLC on the side, the ladder logic, and the laptop you'd be running this on would be directly connected to the PLC, and you just hit download, and you have a real system that is controlled by the real PLC. So other than that, this is practically identical. I have more time. You know what? It would be worth it. Can I borrow one of your CDs? Let me see if I install the, thank you. If I install the full version of CDs. Or, let's start reinstalling the back. All right, I guess that's where. Next, install. We have to uninstall the old one. So give me just a minute, because I'd really like you to see that run. See if it will install. Okay. I'll just show it to you next time. We're going to use a lot of, we're going to be in Logix Pro 5, so we'll worry about it next time. We'll get through these quickly. Because I want to get to one more topic. Okay, the input-output part of the system. All the PLCs have inputs as well as outputs. These are terminals where you connect sensing-type devices, whether it's push button or temperature switch or anything. And you have to wire it up. Okay? So you have to wire up the switch to the terminals on the inputs on the PLC. Now, here's something that you have to get used to. You have to get used to counting from 0 in this class. Okay? Anybody that's dealt with computers before realizes that 0 is also a number. It doesn't like to be skipped. Okay? I feel sorry for my daughter. She's 6 years old, and when we play a board game, I teach her to count from 0. She's going to be an engineer before you know it. Anyway, she's also probably going to be made fun of at school. Okay, so anyway, input 0 is the very first input, and then input 1 is over here, input 2, 3, 4, and so on. Now you notice that the numbers, there may be 16 inputs, but it goes from input number 0 to input 15. Okay. Now normally the way you have to do this, you also have to connect to the DC common and provide a power supply to put power into the input when the switch goes on. Okay. So this is a momentary push button. This is a single pole, single throw switch. I've forgotten what this means and why there's triangle on it. If you guys know, you can tell me. But it's because I've forgotten some schematic symbols. The point is, all of those are input devices, and typically they need power. Output devices typically have a much higher power source, but also usually output devices don't usually turn on a motor directly. Okay, so if this is supposed to be a motor, this would be a fairly small motor because the amount of current you can put through the contacts on a PLC is not terribly small, but not terribly large. So if you want to start a 200 horsepower electric motor, you're not going to run that much current through the output on the PLC. You have to run it through a motor starter, where the PLC controls the motor starter, and the motor starter has larger contactors that can turn on the motor motor itself. Okay? But anyway, there's various excuse me, types of output devices, and in the same way, outputs are labeled from 0 to 15. It's fairly common to see 16 or multiples of 2 input or outputs. Now these are a little bit different because they have, I think, 18 here, and I think analog devices have, no, they do have 8, so that's normal. But anyway, it's kind of odd that the input and outputs on these older PLCs are 18 instead of 16. It's just unique. But there's many different types of output devices that could be used. Now in the past, programming devices, handheld programming devices were used. Those are so difficult to use and so expensive that everybody uses laptops nowadays for programming devices. We already mentioned that. But you may still see a handheld programming device every now and then. This is a screenshot of RS Logix. It looks just like Logix Pro, like I said. But that's basically the software that's used for programming PLCs. Now the program itself, let me go through this. Each one of these things are instructions. Just like you might type an instruction print in a program, right? Or you might reference an object in object-oriented programming. These are instructions, and the way you lay them out determines how it works. Okay? So there's rungs are the horizontal parts. This is called a branch. And I'll show you what all these are a little bit. All right, principles of operation. Here's a mixer process control problem. This is a very simple problem. The mixer motor is to be used to automatically stir the liquid in a vat when the temperature and pressure reach preset values. So the sensor for pressure and the sensor for temperature are on-off type sensors, okay? Pressure and temperature are continuous variables. But these sensors are set to respond so that when the pressure either is above or below a certain amount, the switch will turn on or off. And when the temperature is above or below a certain amount, that switch will turn on or off. Okay? Believe it or not, you probably have some on-off temperature sensors in your home and don't even know it. And how many of you have an oven that you might cook on at home? Well, it turns out that a lot of times the way it's set up, the oven is down below a cook surface on the top. And if the oven somehow overheats the cook surface, you need to cut out power if there's some problem. Okay? So it's common to have temperature sensors that are safety devices, and if the temperature in the underneath the control panel goes above 140 degrees or so, the power to the oven is cut out. So you probably have these and don't even know it. But anyway, manual operation of the motor itself is provided by a push button. Okay, so here's an industrial push button. In fact, I'll pass one around while we're talking about all these things. This is an industrial push button. Instead of being an on-off switch like these light switches, they are momentary switches. That means you push it, it makes contact or breaks contact. You release it, and it changes back. Okay? Instead of being like a switch where once you turn the switch, it stays in that position, these are momentary contacts. Now, in an industrial switch,